Great, then I think we'll get started. Hi, my name is Ryan Hooker. I'm the treasurer for Sigma Pi Sigma who's hosting this lecture. This is Dr. Gong. He's a faculty here at Mines. He teaches the undergraduate quantum course and does research in quantum computing. He's also a NIST associate, and he works with the team up there on an actual quantum computer. And this is his lecture on intro to quantum computing.
Thanks, Ryan, for the introduction. It's a great honor for me to be here today. It's actually the first time I'm speaking to a high school student and non-physics major. So I'm a little nervous, because usually all the audiences are at least physics major or professionals. So I apologize for the title being a little bit different from the poster I saw outside, because that says Quantum Revolution, but there's a subtitle in the poster I saw that says Introduction to Quantum Computing. So it's kind of the same thing, because the quantum revolution I'm trying to mean is really this revolution brought by quantum computers. So we know that classical computers, basically these computers we use nowadays, completely revolutionized our society. So everyone is using them. Your smartphone is basically a computer. And now we have this new generation of computer known as quantum computer. So in this lecture, I'm trying to tell you with the least amount of mathematics what a quantum computer is. Okay, so we're going to start the journey by talking about a game. So we're going to play a little game here. It's a coin game. So this is a game it's like a gambling game you'll play in a casino in Las Vegas. So the game is pretty simple. So you've got a coin that's basically that's heads up, and then you have a computer. So basically you let the computer play first. So the computer will play a move, and the move computer plays will not be known to you. So the computer can basically keep this coin untouched, or it can flip the coin. So it has two choices, but you don't know the answer. And then after the computer plays, you are going to play. So you can tell the computer whether you want to flip the coin or not. So also, your choice will not be known to the computer. So, and then the next step, the computer will play again. So the computer can choose to flip or not flip the coin again. And at the end, we're basically going to reveal the answer by looking at whether the coin is heads or tails. And if the coin is heads, then the computer wins. If the coin is tails, then you win. So it's a very simple game. So it's kind of a little boring game. But the question here is, so what is the probability that you're going to win the game? So anyone wants to make a guess? This is nothing quantum. It's just a very simple thing. Okay.
50%.
Okay. Anybody else? Anyone agreeing with 50%?
Around 17%.
17%? That's a pretty weird number. Okay. Should we do a vote? How many of you agree with 50%? Okay. How many of you are not agreeing with 50%? I see. I'm probably going to say somebody. I'm not going to vote on any one of this. Okay, so here is what happens if you really do this experiment. So somebody actually did this experiment. They just basically let a lot of students doing this game, and this is what the result looks like. So the player wins 53% of the time, the computer wins 47% of the time. And this is because we don't actually run this game for enough number of players. If you actually increase the number of players, this probability will actually goes to 50% for the player and for the computer. So it's a pretty fair game, because you don't actually let the computer knows your move, and the computer's move you don't know, so it will be a fair game. So theoretically, you have a 50% chance of winning the game. It's like a pure luck gambling. Okay, so now the interesting thing is, what if the computer in the casino is actually a quantum computer? So I'm pretty sure that Las Vegas you don't have any quantum computers in the casino, but assuming we actually have a quantum computer, and we do have ones already. So actually, IBM is making some of these quantum computers, so this looks pretty complicated, but at the end you can actually access this type of quantum computer just from the cloud, just using your web browser. And you can play that game by replacing the computer there by a quantum computer, which is running by IBM at this moment. And guess what happens if you do that? So actually this experiment is also run on this quantum computer, and this is the result. Oh, sorry. This is the result. So the quantum computer wins 97% of the time, while the player only wins 3% of the time. And that 3% is only because the quantum computer has an error rate of 3%. So if the quantum computer is performing perfectly, you're not going to win at all. the player is not going to win at all. So this seems like magic. So what's really happening? It seems like the computer is cheating, but it's actually not. It's simply because this computer is using the power of quantum physics, and that will make the player losing all the time. Okay, so here's what's happening here. So a coin has two sides, heads and tails. So the computer processes this information by using just 0 and 1. So the computer doesn't know if it's heads and tails, but it knows whether it's 0 or 1. So that's how our computers process and store information. It's in the unit of bits. And a bit can either be 0 or 1. So that's what's happening inside a traditional computer. But in a quantum computer, things are slightly more complicated. So instead of just being 0 and 1, in a quantum computer, a quantum bit can actually be in a combination of 0 and 1. So you can actually have something that is a combination or superposition of heads and tails in a quantum computer. So you can store this kind of information. So if you find it hard to understand, you can basically think about that coin as a spinning coin. So a coin has heads and tails, but if you spin the coin, then you actually don't know whether it's head and tails. You can think about it as a simultaneous state of being heads and tails. Because if you actually stop the coin, it can either be in heads or tails, each with half probability. So we call that a superposition state. And quantum computer can actually make this type of state possible. So you can store the information of the coin in this superposition state. And you can also make the coin in such superposition states. So here is why you will always lose to a quantum computer. So first you start with a coin in heads, and then the quantum computer is not going to simply flip the coin. It's going to make this coin to be in a superposition state of heads and tails. So it becomes a spinning coin. And then, if you have a spinning coin, if you flip the side of the coin, so if you actually flip the heads and tails, it's still going to be a spinning coin. Actually, that spinning coin is not going to change at all if you flip it, because it's keep rotating, right? If you flip it, it's still rotating in the same fashion. So that means whatever you do, whatever you choose to flip or not flip, that spinning coin is the same as the spinning coin the computer achieves. So you're not actually doing anything. And then the computer sort of cheats by just redone the process of going from here to here. So the computer just reverses this process, so he's always going to get heads. So in this case, the computer will win 100% of time, and you lose 100% of time. Unless the computer has some error. So you can't do this process perfectly. Right? Okay. So here is a remedy to this computer cheating problem. So if you also have a quantum computer, so if I also have a quantum computer, and the move I play here can also use the power of a quantum computer, then I can make the quantum computer lose 100% of it. So here's how I do. So if I have a quantum computer, so I'm not going to flip the side of the coin here because it's a spinning coin. If I flip it, it's not going to change anything. But what I'm going to do is I'm going to change this h plus t to h minus t. So it's kind of a different superposition of the heads and tails. So if you find this hard to understand, this is kind of like reverse the spinning direction of the coin. So if it's spinning clockwise, now I have a quantum computer, I can spin it counterclockwise. If I do that, and the computer is still trying to reverse what he did, he's going to end up with tails all the time. If you reverse the spinning direction, that's what happened for a quantum computer. In that case, you will win 100% of the time. 100% of the time. Okay, so that seems to be a fun game. But of course, quantum computers are not just used to win this kind of unfair game. That's not the main purpose of a quantum computer. But this is really trying to introduce you what's really happening inside a quantum computer. Because a quantum computer is storing information in a special type of bits called quantum bit. And the major difference of a quantum bit from a traditional bit is that it can actually be in a superposition of 0 and 1. And the coin here is really just an energy of that. Okay, so let's get into more details of what a quantum bit is. So a classical computer, as I just said, processes information in the unit of bits, which can either be 0 and 1. So each bit is either 0 or 1. It cannot be anything else, otherwise your classical computer must be malfunctioning. Usually the 0 and 1 is represented by some, whether a current flows through a transistor or not, or whether the voltage is high or low in a transistor. So it's a binary state. It's a binary information. And a quantum bit will be the building block for a quantum computer. So basically a quantum computer can have many of these quantum bits. But each of these quantum bits can actually be in a combination of 0 and 1. So this is sort of the fundamental difference between a quantum computer and a classical computer. So as we said before, so if you use this analogy of heads and tails of a coin as the two states, now you can actually be in this superposition of heads and tails. And actually this superposition, you can change this coefficient as well. So this alpha and beta can be any number, and they can even be complex number. So you can see this color I'm trying to illustrate here can actually have sort of like a gradual change from blue to yellow, depending on the percentage of alpha over beta. So you can actually have a smooth interpolation of 0 and 1 in a quantum computer. So naively, we can just write this as alpha times 0 plus beta times 1. But that's kind of like a really awkward notation. If you really think about this as algebra, this should add up to just beta because alpha times 0 is 0. But that's not the correct way of doing it. So here, the 0 and 1 really means two states, basically two different values of the quantum bit. So physicists tries to be more rigorous on the notation, so not to confuse you with this equation. So actually, they put a little bit of bracket on this 0 and 1. So this little bit, so this 0 with this bracket, within this bracket actually means the quantum bit in the state 0. And that bracket means a quantum bit in state 1. So it's just a less confusing notation than just the number 0 and 1. So a quantum bit can be in a superposition of 0, 1. That's sort of the first take-home message of this lecture. Okay, so the next question is, so this is all like just theoretical. So this is just how a quantum bit works in theory. But how do physicists actually find quantum bit? So are there anything in nature that can be used as a quantum bit that can actually be in a superposition of two different states? So that's a key question. This has to eventually be realized in the lab. And it turns out one of the best candidates for a quantum bit is just a photon. So what is a photon? So first, I think everyone knows that what is light. So light is some kind of electromagnetic wave. And the light can diffract, it can refract, it can also interfere. This is what we see in everyday life. And for some reason, light is also made of photons. So photons are actually the smallest constituent of light. So it sort of behaves like a particle. So this might sound new to some of you, but then think about this sort of experience you have if you take your cell phone and take a picture with very low light. So this is what will be happening. You'll basically see an image with a lot of noise, with a lot of these dots here. It's basically this color noise. So what's really happening here is when the light gets very weak, so basically it's very dim, then the light no longer behaves like waves. So it's actually these tiny particles that forms the light, which are known as photons, that's hitting your camera sensor. And because these are particles, you're going to see noises, because these particles can hit this portion of the sensor or that portion of the sensor. And this sort of particle behave picture will basically result in these noises you see in the images. So these noises, you can sort of see this remnant of these photons. So basically they're hitting the camera sensor. And this is something physicists realized more than 100 years ago. So light is actually made of photons, which are the smallest constituent of light. And the word quantum, which is the word we use in the title, so it just means the smallest amount of physical entity. So in this case, a photon will be a quantum object, so it's a quantum particle for light. And similarly, an electron and an atom are also quantum particles because an electron, you cannot divide it. Electron is the smallest constituent of an electric current. So that's the smallest physical entity that's moving there when you have a current. And similarly for an atom, you can't really divide an atom into two half of the atoms. So that can't be done. So these are all quantum particles. So we're not really going to go to all the details of the quantum physics, but we're just going to say that these very small particles that cannot be divided any further obey rules dramatically different from the objects we see in everyday life. All these big objects, we call them classical objects like the table or like your cell phone, like the chair. So these, of course, consist of many, many particles, maybe millions and billions of these particles. But if you're only looking at very small number of particles, just one of them, then the rules governing their world is dramatically different, and that's sort of the realm of quantum physics. And the rules governing the big objects in our world are basically your familiar Newton's laws. So they're very different. And sort of one of the most important differences, these quantum particles can actually be in this superposition state. So this is not possible for classical objects. For example, a chair cannot be a superposition state of being, both here and there. So that's impossible. Okay, so let's talk a little bit more about photon. So I'm trying to have some kind of everyday understanding to the superposition state of a photon. And you can actually sort of understand it just by some kind of experience in life. So I think, had anyone played around with polarized sunglasses? I think, okay, okay, that's good. So if you know polarized sunglasses, then you should know that the light we see has a property called polarization. So basically the polarization means the direction of the oscillation of the light wave. So basically it's an electromagnetic wave. So this oscillation, for example, can be in the vertical direction like this, or it can be in the horizontal direction like that. So basically in the horizontal plane here. So this polarization, so if you just look at the light from the sun, so that light actually has polarization in every direction. But if you put a polarized sunglass, so it's also called a polarizer, then only the polarization of the light that's aligned with the direction of the polarizer or your sunglass will pass through. So that's what happened. So this is a polarizer. So this can be just taken from your polarizing sunglass. So you can see that the light passing through the polarizer to the piece of paper will basically be dimmer than the light that's shining on the paper. That's because only the part of the light that has the polarization aligned basically in this direction. So this handle here actually tells you the direction of the polarizer. So only the light polarizing in this direction will actually pass through the polarizer and gets to the paper. And here we have another polarizer that's on top of this polarizer, and this one's got a horizontal handle. So that means only the light that's got polarization that's actually oscillating in this direction will going to pass through this polarizer. So this is something you can actually experiment yourself. Just get two polarized sunglasses and just make them perpendicular and see what's the light passing through them. But what is interesting is because these two polarizers have 90-degree direction of their polarizer, you actually see basically no light going through both of the polarizer. And the reason for this is the light going through this polarizer, the top polarizer is going to be polarizing in this direction, and for light polarizing in this direction, it cannot pass through the second one, the one in the bottom, because that one can only pass light with polarization in the vertical direction. And because these two are orthogonal, you basically get no lights passing through both polarizers. By the way, if you have any questions, feel free to stop me. So I'm trying to keep this talk as elementary as possible, so just feel free to stop me if you're confused about anything. Question?
You mentioned earlier about alpha and beta representing multiples for the states 0 and 1. Alpha and beta have to sum to 1, correct?
That's a good question. We'll get to that very soon. You'll see that just in this example using photon. That's a very good question. Question?
Transistors in the computer, it's either on and off, voltage or current. You said that.
Yep.
And how could the transistor be in a superposition state?
That's a good question too. The transistor cannot be in a superposition because it's not a quantum object. A transistor is made of many electrons atoms. So it's actually it's like our everyday big object. So it cannot actually be quantum. So it cannot act as a quantum bit. So in order to make a quantum bit, the one that can actually do a superposition of 0 and 1, you have to use these tiny particles such as a photon. So this is why we're going here. Right. Any other questions? Okay, let's continue the journey on the light or photon. So what we learned from here is a photon can be polarized either horizontally or vertically, and we can denote these two states by this H and V. So the H stands for horizontal and V stands for vertical. We're putting this funny bracket just to just to denote that it's a state of the photon. It's not just a letter H or letter V. And these are just two distinct states of photons. So if the photon is horizontally polarized, it cannot pass a vertical polarizer. So these two are just not, they're basically orthogonal. They're very different. But then you can naturally think about this question. So a photon, because this is a polarization, it's just the direction of the oscillation. I can actually polarize a photon in any direction. So it doesn't need to be horizontal or vertical. It can be any angle theta from, say, the horizontal direction. Right? I can polarize. I can actually have light that's polarized in this direction. That's totally fine. I can actually find light like this. And then, if you try to represent the state of the photon here, it will naturally be a superposition or combination of the horizontal and vertically polarized photon. This is just a geometry. You get cosine theta of H plus sine theta of V. So it's basically, if you have this direction, you just project that into either the horizontal axis or the vertical axis. Here you get a cosine theta, and here you get a sine theta. So you can always write that as a sum of horizontal and vertically polarized. Okay. So here's a question I would like to ask you. So suppose I just take theta to be 45 degrees, so which is just halfway between horizontal and vertically polarized. So this would be the case if I make one of these polarizer 45 degrees from the second one. So look at the handle, that's the direction. So that means the sunlight that goes through this polarizer will be polarized in this direction, which is exactly that 45 angle I'm drawing here. So that means the photon that pass through this polarizer will be in the state of cosine 45 degree times the horizontal polarized state and plus sine 45 degree times the vertically polarized state, right? And now the question for you is, I put this polarizer on top of this one. So what will be the brightness of the light that hits the paper when I overlap these two? Right? If these two are, so let's just go back here. So if these two are 90 degrees, you can see that overlapping area is completely dark. So no light is going to make through the paper. And now if it's 45 degrees, so does anyone want to make a guess how much percentage of the light will go through the second polarizer and hit the paper? Anyone?
Half.
Half? Okay, that's a good guess. Anybody else?
30%.
30%? Okay, that seems more random.
What percentage of the light will pass through both?
Yeah, pass through both and hit the paper.
25%.
25. Okay, that's also a reasonable guess.
75.
75. Okay. 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 So let me reveal the answer. So actually, the answer is pretty simple. So don't overthink. The answer is just 50%. Okay. It's actually sort of very, very simple because if it's 90 degrees, you get 0, and if it's 0 degree, that means you're not doing anything. It's just 100%. And 45 degrees is exactly in the middle of the two. So that's 50%. And this is something you can really do yourself to check. Okay, so here's a funny thing. So this is really for light, and as I said before, light is made of photons. So for each photon, it's not divisible. So there's no half photon in the world. So for each photon, so it has to either pass or not pass the polarizer. For example, not pass the second polarizer, right? It has to choose whether to pass or not. It can't split into halves. So how does this 50% come from, right? Because you can't. There's no half photon, and the thing that's really happening is that each photon has 50% probability of passing this vertical polarizer, the second polarizer here. So half of the photon will actually not pass, and the other half will pass, and it's kind of randomly chosen. So each photon basically has to throw a dice, right? If it's favorable, then it's going to pass it. So it's a 50% chance of passing it. It's not half of the photon passing. So that's something we have to verify. And so here I want to do some little bit of math here. So how do you get this 50% in reality? As we said, the state of the photon passing through the first polarizer is given by this cosine 45 degree of H and sine 45 degree of V. And we know if the photon is really in the V, it's going to pass through this. So how does that sine 45 degree end up related to this 50%. And you can do a little bit simple, do a simple math here. The sine 45 degrees square is equal to 1 half. Because sine of 45 degree, that's 1 over square root of 2. So if you square that number, you get 50%. So what's really happening is the square of this coefficient gives you the probability for the photon to actually pass through the vertical polarizer. So that's the physical meaning of the superposition state of the photon. Okay, so if you generalize this a little bit, you can see that if I have some arbitrary angle theta other than 45 degree, then the photon passing through the vertical polarizer will be sine square of theta. So I'm just replacing 45 degree by theta. And then if actually this polarizer is horizontally polarized, if I rotate the handle here by 90 degree, you will find the probability of the photon passing through this horizontal polarizer will be given by cosine square of theta. So basically given by this coefficient squared, because now I'm checking whether the photon is horizontally polarized. So it's basically given by the corresponding coefficient squared. So that would be cosine squared theta. And the nice thing about this is these two actually adds up to 1. So that sort of makes sense, right? Because the photon can either be horizontal or vertically polarized. And the probability of doing both has to add up to 1. So you can see the sine squared theta plus cosine squared theta has to be 1. So that goes back to your question you just asked. The probability is not just given by the coefficient. It's actually given by the coefficient squared. So that's the answer to that question. So it's a little bit more subtle than just the coefficient. And there's a reason for that, because this coefficient can actually be negative. So as I mentioned in this coin game, I can actually try to defeat the quantum computer by changing the H plus B state to H, by changing the head plus tail to head minus tail. And the minus really means the coefficient here can be minus. As we know, the sine theta can also be minus. So you have to square it. And in reality, these can even be complex numbers. And we're not going to go to the complex number in this lecture. But for complex number, you can also take the absolute value squared. So that will be a positive number. So that's why we need the square, just to count for negative coefficient or complex coefficient. Any questions? Okay.
So, what percentage of the photons pass only through the 45 degree lens?
Oh, you mean from the sunlight?
Yeah.
Yeah. So that one we actually don't know. I think it's 50% as well, but we're not going to because the sunlight contains a mixture of all polarizations. So usually it's 50% in this case. But that's a different question than what we are considering here. We're only considering the portion of the light that already passed through the first polarizer, but gets to the second.
Okay.
Question?
As I understood, superposition is two events could happen at the same time.
Yep.
But I don't see it here. I see if you change the event based on the polarization of the other filter. You change the polarization, you make different percentage. They cannot happen at the same time.
That's also a very good question. So what's really happening here is, so what this second polarizer is doing is doing a measurement on whether this photon is vertically polarized or not. So you can see that before the measurement, the photon is really in the superposition state of H and V. We'll get to that in the next step. But after you make that measurement, after you let it pass through the second polarizer, the photon has to determine its fate, whether it wants to pass or not to pass. But before that, it doesn't need to do it. So it's a superposition state. But after you have to make that choice, it's basically like a measurement. So basically asking, are you really in horizontal or in vertical? Right? So it's like asking the qubit, are you really in 0 or in 1? Right? And then you have to answer that question. Right? So before you answer the question, I can say I'm in the superposition. But if you ask you have to tell me a definite answer. Because what you actually see in the measurement has to be something specific. Right? Okay, so let's try to summarize a little bit about the qubit, just from the knowledge we learned about a photon and this polarizer experiment. So a photon with two orthogonal polarization H and V can basically serve as a qubit because it can be in a superposition state of horizontally polarized and vertically polarized. That's basically a polarization direction somewhere with an angle theta from H and B. So you can see this basically takes the form of alpha 0 plus beta 1. So the 0 here will basically correspond to the horizontally polarized photon, and the 1 here will correspond to the vertically polarized photon. So you can really encode one quantum bit of information by just using a photon that's either horizontally polarized or vertically polarized. So you can see a photon can really serve as a qubit, and actually researchers indeed use photons as the early platforms for quantum computers. Right now they have better ones, so this is kind of like already somewhat outdated, but this still serves as a very good pedagogical example of what can actually make a quantum bit. And then going back to his question, so a quantum bit can be in a superposition of 0 and 1, but if you really want to measure the quantum bit, you want to ask, are you really in 0 or really in 1? Then what's happening is that you will have a probability of the alpha squared to find the quantum bit in 0, similar like what we did in the polarizer experiment. And then you will have a probability of beta squared to find the quantum bit to be 1. So it's really a probabilistic choice of either being 0 and 1. So that's what superposition really means in physical reality. And what is also interesting is after the measurement, the quantum bit will no longer be in the superposition state. It will either be 0 or 1, just like the classical bit. So you can try to understand it by thinking about that photon, right? So that photon is in the superposition state before it passes through the second polarizer. It's basically in this superposition state. But after you let it pass through it, it's kind of like a measurement. The photon has to decide whether to pass or not. If it passes it, then it has to be vertical polarized, because this polarizer will only make lights that are vertically polarized to pass it. But if it doesn't pass it, that means it has to be horizontally polarized, so that will get completely blocked by the polarizer. So after the measurement, after you're trying to measure whether it's horizontally or vertically polarized, it will end up being either one or the other. So you lose the superposition after the measurement. And this is pretty much all you need to know about a quantum bit. So it seems very exotic, but the underlying rules are really not so complicated. So first you can be in a superposition of 2 states, and then when you measure it to find out whether it's in 0 and 1, you get these probabilities. And after the measurement, you lose the superposition, you get either 0 or 1. So that's sort of the 3 rules for a quantum bit, and that's pretty much all you need to know for a quantum bit. That's a building block for a quantum computer. Okay? Any questions?
Actually, photon is an elementary particle, and how does it correlate with, say, like a phase angle with amplitude and magnitude? How's that? Is that calculated, or am I?
That's also related. This is something we ignored. So I said this alpha and beta can actually be complex numbers. Okay. So the phase angle you're talking about is basically going to add a complex e to the I phi, a phase, to this term. Okay. Right. So that will actually show up, but we're going to ignore complex numbers here, just for simplicity. It does play a role. Question?
I'm just trying to restate what you said to make sure I understood.
Okay, sure.
Once the light passes the second polarizer, we are expecting it to be vertical. But when we do the measurement, it could be vertical, could be not. Is that what it is?
Yeah, it is. But if it's horizontal, it will get blocked, and you won't see it on the paper. So that's what happened, right? So what you see, that 50% brightness is caused by the photons that pass through the second polarizer, and that has to be vertically polarized, right? So the light you see on the paper are basically shined by all the photons that are vertically polarized, and the ones that are horizontally polarized will get blocked, basically get absorbed by the polarizer.
And the measurement will show vertical.
So the measurement here
on the paper, I mean.
Yeah, exactly. Will basically be the vertical ones. The horizontal ones you won't see it. In order to see the horizontal ones, you have to rotate this one 90 degrees. And
but
then you will see the horizontal one.
I mean, it is expected thing. There is nothing spooky here. I expect
There's nothing spooky when you look at the light. That's definitely correct. But if you look at each individual photon, that's really probabilistic. It's totally random, because each individual photon has to either pass or not. And that 50% chance is what makes things random. Right? So if you just look at this, you always get 50% brightness. But if you really look at this tiny constitution of the light, which is this individual photon, And that one's fate is not determined. You have this 50-50%. Right? That's a very good question. Any other questions before we proceed? Okay.
The 50% of the light that passes through specifically refers to the photons that successfully passed through the first polarizer.
The second one. The first one, we're assuming...
Or rather, we are assuming when we say 50% of the light passes through the second polarizer.
Yeah, this 50% is only compared to this. So it's 50% of the light that already passed through the first one.
Ah, all right.
Yeah. Okay. No more questions. Let's go to more than one quantum bit. We're going to go crazy pretty soon. Okay. So let's go to many qubits. So as we said, one quantum bit can be in a superposition of two states, basically 0 and 1. So what about 2? So 2 quantum bits can be in a superposition of basically 4 different states. And that will be 0, 0, 0, 1, 1, 0, and 1, 1. Again, I'm putting this funny bracket just to make sure that this is not just 2 numbers, 0 and 0 together. And you can see I have 4 coefficients, so alpha, beta, gamma, and delta. You can see that I'm going to quickly run out of these Greek letters and add more quantum bits. Right? Okay, so here's a question for you. So if I have 3 quantum bits, so they can be in a superposition of how many states? 8? Anybody saying 6? These are the only 2 possible answers, right? Either 6 or 8, right? It has to do with the number 3. Okay, so I think most of you get it right. It's 8 states, so don't get the 6. If you get the 6, that's not right. You can try it. So if you have 3 bits, it's going to be 0, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 0, 1, 1. And you can keep counting it. It will be 8. Trust me. Okay? And then if you try to generalize this, if I have n quantum bits, they can be in a superposition of 2 to the n states, right? Because for 3, 2 to the 3 is 8. So if I have n of this, there will be 2 to the n different states made of these 0 and 1s. So you can be in a superposition of 2 to the n states. And that 2 to the n is a really crazy number. So you might not actually have a feeling of it. Let me give you some example. So if you have 30 quantum bits, which is really small, classical computer has like, you have gigabyte storage, right? Or terabyte storage, that's like 10 to the 12. Right? It's much more than just 30. So for 30 quantum bits, there is going to be more than 1 billion states. So look at that, you got basically 9 digits after 1. And if you try to have 300 quantum bits, so they can be in a superposition of how many states? So this number is 10 to the 90. So it's a crazy number. So it's basically, you have 1 with 90 zeros. So it's a number larger than that. And that number is larger than the total number of atoms in the universe. The total number of atoms in the universe is roughly 10 to the 80. And this got 10 more zeros after that. So that's a crazy amount of number. That's a really big number with just 300 quantum bits. And these are not really crazy. Think about each photon can be served as a quantum bit. You're just putting 300 photons together, or 300 electrons. Right? So it's nothing gigantic. But it's just the number of states they can be in, and superposition is crazy. So then, now we can think about some magic. So think about quantum computer as a device that can actually do calculations on this superposition state. So if you send a state of n quantum bits, they can be in a superposition of 2 to the n different states. If you send it to the quantum computer, it's going to calculate all the 2 to the n components simultaneously. So that's what's going to happen. And that means compared to a classical computer, that seems exponentially faster. So a classical computer, if you have, for example, let's just take the example of 2 qubits here. So I have 0, 0, 0, 1, 1, 0, and 1, 1. So I want you to calculate some function f of x. So it could be anything, it could be sine of x, it could be anything. And then for a classical computer, I have to first calculate the function for the input state of 0, 0, and then calculate for the input state of 0, 1, and then 1, 0, and 1, 1. I basically have to calculate 4 individual terms. in order to actually know the sum, the function of the sum of this, right? So if I have n quantum bits, I have to calculate 2 to the n individual terms on a classical computer. But a quantum computer, because these are just 2 photons, I can send it into a quantum computer, and because it's in the superposition state, the quantum computer is going to process that superposition state just in one step. So it's going to output a state that will basically change each of these input to the function of that. So this can be done in one step. So even if you have 2 to the n component, you can do this calculation of a function in just one step. So this is sort of the source of the power offered by a quantum computer. So you can immediately see from here that the quantum computer are supposedly to do much faster, to perform much faster than a classical computer, just because you can actually process 2 to the n different inputs in one time, in one step. Okay, so this seems really powerful. If this is the case, that means quantum computers can run exponentially faster than a classical computer. So exponential basically means if you have n quantum bits, it's going to be 2 to the n times faster than a classical quantum computer. And remember the crazy number of 2 to the n. So if you have n to the 300, that's like almost, that factor is larger than the number of atoms in the universe. But unfortunately, this is too good to be true. So if that's the case, we won't have any computers now. So it will all be replaced by quantum computers. But there's a catch to this, and this catch you can actually understand it because we told you what, you know, how do you measure a quantum bit? What happens when you measure a quantum bit? So the catch is this. So you can let a quantum computer calculate all these components for you, but at the end, you have to read out the answer of the quantum computer. So you have to measure the output, and when you measure the output here is also in the superposition of basically 4 states here, and you have n quantum bit, it will be 2 to the n states here. And when you measure it, you will only get 1 out of the 2 to the n result, right? So like when you measure the photon with 2 different polarizations, you only get 1 out of it. It either passes through the polarizer or not. Right? Think about that experiment. You only get 1 result out of the 2. But now if you have 2 photons or 2 qubits, you will only get 1 result out of the 4 at a time, right? So if you have n quantum bits, you will only get 1 out of the 2 to the n possible outcomes at a time. And then that means if you really want to figure out all these calculation values, you have to measure 2 to the n times, right? So even though you can calculate in one step, you have to measure 2 to the n times, and that completely kills the speed up, right? Because you just need to run the quantum computer for 2 to the n times and measure it. So every time you measure it, you basically destroy the superposition. In order to measure it again, you have to restart your quantum computer and do it again. So if you do 2 to the n times, that completely kills the speed up, right? So it seems like this naive exponential speed up is just too good to be true. But the physicists are clever. So this naive way doesn't work, but you can actually find some way to cleverly utilize this massive exponential speed up offered by a quantum computer. So we're not going to go into super details about that because this can get really complicated. But I'm trying to give you sort of the essence of what physicists are really trying to do. So we can design something called a quantum algorithm, similar to an algorithm on a classical computer. Right? It's basically some kind of, some kind of code. You can think basically like that. So what that does is, so I'm not going to just end up here. If I end up here, I'm only going to get one of these outcomes. But I'm going to keep doing some functions here, some evaluations here, until I get to the result that these other coefficients all becomes 0. So for this case of 2 quantum bit, I want to make sure that 3 of these coefficients actually becomes 0 at the end of the calculation result. In that case, I will only end up with 1 of these components. So if I measure it, I will get the result 100% of the time. So that's sort of idea. I want to cleverly put my final answer into just 1 of these components and make all the other components have 0 coefficient. So if I do that, when I measure it, I get 100% the result I want. I don't need to repeat the measurement. I don't need to restart my quantum computer. Of course, that's very hard. It really depends on what kind of problem you want to solve on a quantum computer. You have to design a dedicated algorithm to do that. But in some cases, it does work. And I'm going to show you examples of in what cases it really works and can give you dramatic speed up compared to classical computers. Okay, any questions before that? Okay, so let's look at the applications. So the first application is actually the most universal one. It's just database search. So we are doing that almost every day on our cell phone, on our classical computer. And when you're doing a search on Google, it's going to search through basically billions of items in the database. So just think about that. You have, for example, a lot of these boxes, and you want to find a pink one out of n of them, and the n could be 2 to the some little n, which could be some gigantic number, say a billion. So a classical computer, how does it work? So in the worst case, it's going to search through all these boxes one by one. So it's going to ask whether the first box is pink or gray. If it's not, it's going to go to the second box until you hit that pink box. And that pink box could be at the last one. Then you're pretty unlucky. You have to search through the whole list of the boxes. But on average, you can see you have to basically search through on the order of n boxes. So basically, the time it takes to do this database search is proportional to n. So on average, I think it's n over 2 to find the item in this unstructured database. And here is sort of what quantum computer can do. I'm not going to tell you the details. It's called the Grover search algorithm. You can actually design an algorithm that let the quantum computer only run for a time that's proportional to the square roots of n. So the square root of the number of the items you want to search through. So that's a lot faster. It's not exponentially faster, but it's still a lot faster. If n is equal to, say, 1,000,000, and then the square root of n is only 1,000, so you are getting a speed up from 1,000,000 seconds to 1,000 seconds. That's pretty spectacular. And it goes, and you can see that speed up becomes more and more important when the n is large, when you have a really big database to search. And sort of the idea there is similar to what I just said. So what's happening is initially you are going to send a superposition of all these n states, so all the 2 to the little n states, to the quantum computer. And then the quantum computer is trying to basically process which one is a pink box all at once. But that doesn't work because you get a superposition of the answer and you have to measure 2 to the n times. But then you have to do some more complicated operation on the quantum computer to make sure all the coefficients before these wrong items get smaller and smaller when you run the quantum computer. And the pink box, the one corresponding to the pink box, will get a coefficient that becomes larger and larger until all the other ones get to 0, and that one becomes 1. And then you measure it, that's the answer. So that's sort of the idea. And the number of steps you have to do this is basically proportional to square root of n. So that's how the search algorithm works. And because search is such a ubiquitous operation in computing, so quantum computers can almost do any complicated task using this search algorithm quadratically faster than quantum computers. So quadratic basically means this square root here. So that's already an important application of quantum computer. So the square root speed up or the quadratic speed up is sort of the most universal application quantum computers can offer. But if you're not satisfied with just a quadratic speed up, there's something more. So this is probably the most dramatic application of quantum computers. So this is for factoring numbers. So basically, if you have a number I want to factorize into two prime factors. So think about the number 21. So I can factorize that into 3 by 7. So that's something anyone can do. But then if I give you a very large number, for example, this number, 70, that's 7,323,629. So if I ask you to factorize that into 2 prime numbers, that's going to take you a long time, right? How am I supposed to do that? I can tell you the answer is going to be given by these 2 crazy numbers. But the interesting thing here is if I give you these answers, you can check whether these 2 are actually the factors of this big number. Pretty easy. You just use your calculator. I can do it in 2 seconds. Just multiply these 2 numbers. I can see whether it's equal to that. So this is a really interesting question. So if you have a very large number, try to find the 2 prime factors for that is really, really hard. And to give you an example, you have a 200-digit number. So that's a pretty long number. It will actually take a computer with a single core GPU of 2 gigahertz, 2,000 years to factorize it. So that's a crazy hard problem. But once you have the factors, if you know these factors, checking the answer just take a couple seconds using the same CPU. So you can see that what is interesting for this type of problem. So this is very useful for cryptography. So what this is for is, so you can actually use these factors as your private key. So this is basically your key. And the large number is something called the public key. So if you want to transmit information, a message securely to somebody else over the internet, you can just let everyone know this big number. But the key is actually the small numbers that are the prime factors. And nobody can really calculate this in a reasonable amount of time if the number you give is really large. But you have the key. So if you want to open this message securely, you can just enter the key, and the computer can check whether this is the correct key very easily. So that's actually a system used almost ubiquitously on the internet. So if you just log into your bank, log into your email, most likely the cryptography system is based on this factorization of large numbers, and this is called the RSA cryptography system. It stands for Three Computer Scientists last name. Okay, and the good news is if you have a quantum computer, or maybe the bad news, if you want, if a quantum computer can really factorize these large numbers, then that means all these, security systems becomes insecure. To give an example, for this 200-digit number, if you really have a quantum computer that's running on the same speed as a classical computer, in terms of the CPU frequency, you can actually factorize such number with just a couple of seconds. So that means all your bank credentials are not safe anymore if you really have a quantum computer that powerful. So this could be a good news for some people and bad news for the others. For that reason, almost the government of all the big countries are now putting a lot of money into this. You can immediately see the military importance of this just because of this cryptography system hacking possibilities. And because this is really exponentially faster in the sense that the quantum computer can take a time that's exponentially shorter than a classical computer. So here we're actually using the full exponential speed of our quantum computer. So that's a really clever algorithm design. Okay, so the last example, perhaps less harmful, is for quantum chemistry. So in chemistry, in biology, and also in medical science, people want to find molecules with good properties. But it's very hard to actually find and make these molecules because it's just very hard to model them on a classical computer and simulate their properties, because usually you want to model them on a classical computer first to simulate their properties before you actually go to make them. And the reason is also very simple, because a molecule is made of hundreds and thousands of these quantum particles, such as electrons or atoms. And as we said before, for each of these quantum particles, the simplest one will be this quantum bit, you will need 2 to the n bits to track the states, right? You have that many states. You have 2 to the n states of that n quantum particle. And you can see that a traditional computer like this will quickly run out of memory, just because like 2 to the n is a huge number. You have that many states to keep track of. For n equal to 30, that's already a billion. So you already need more than a terabyte memory on a computer to just store the states of a molecule of just 30 electrons. So that means it's almost impossible to do it on a traditional computer. But a quantum computer can do this. And the reason is very simple, because the constituents of the quantum computer are actually made of these quantum particles, such as the photons we talk about. So these are quantum bits, and each quantum bit can pretty much simulate one of these particles in the molecule one by one. So if you want to simulate n of these particles, a molecule of n of these quantum particles, you just need a quantum computer with n quantum bits, roughly on that order. So that's a pretty modest cost. If you have a 300 particle molecule, you just need 300 or maybe 600 quantum bit quantum computer to do it. That's a lot better than needing like tens of terabytes of memory on a classical computer. And you can also do things a lot faster just because the amount of memory you are saving. Okay, so where are we now? So we talk about these interesting potential applications. So what are the quantum computers that are already available and made in the lab? So here is one of the leading quantum computers made by the IBM. I sort of mentioned that picture early on. So right now, they have a quantum computer made of just 20 quantum bits. So you might think 20 is a small number, but again, think about that 2 to the 20. So you can actually calculate 2 to the 20 states simultaneously in one step. And that number is 1 million. So it's actually not that small. And this is not, so you have to be their client to use it. So you have to pay a premium for using that. So even though it has 20 quantum bits, this still wouldn't be dramatically useful at this moment, because for 20 quantum bits, you can still basically do any calculations on your classical computer faster, just on your laptop faster than this one. But you can see that if I increase this number, it will beat the traditional computers very fast, just because that exponential growth. So if you have a 100 qubit quantum bit chip like this, it will basically outperform any supercomputer in the world. And this is something people call a quantum supremacy. So basically, it's the time that quantum computers basically outperforms any classical computer in the world. So we're actually pretty close to that. So probably just a couple of years from now. But one thing I need to mention is the quantum computers at this moment are actually far from ideal. They're actually much worse performance than the classical computer in one important aspect, which is the error. So as I said in the very beginning, for the coin game, you have this 3% error for the quantum computer to fail, and that is only for one quantum bit, right? So now you have 20 of them. This error rate actually grows up very fast, and the error rate is about 1 to 10%, depending on different operations, just per every elementary operation you are doing on a quantum computer. This could just be adding two numbers, so you get 10% error of doing it wrong. So that's actually pretty big. Right? If you do 10 number adding, you will basically have almost surely one of them failing. And the other bad thing is this quantum computer has to restart after every 500 elementary operations, which is also kind of funny because a classical computer you can run it days and days, you don't need to restart it. And a quantum computer you need to restart it pretty quickly. And you can see the CPU frequency for that is basically 5 gigahertz. That's pretty quick, but you can only run for 500 elementary operations, so you have to restart it every 1 in 10,000 seconds. So you have to restart it pretty frequently to make it work. But even with all these constraints, if you can actually make a 100 qubit chip of that, it's going to outperform any classical computer in the world. So that's sort of the exciting news. Okay, so at the end, I have some sort of one thing for you, which you should, which I hope you can try. So this is actually a website offered by IBM. So this is free, so everyone can try it. It's kind of hard to see it, but if you just Google quantum experience, you will find this website. So you can sign up for a free account, and you can actually play around with these 5 quantum bit quantum computers made by the IBM yourself. So it's on the cloud. So you can actually, so there's all these parameters here, and this is sort of what the chip really looks like. So you basically have 5 quantum bit here from 0, 1, 2, 3, 4. So there's 5 of them. They're initially all in state 0. And I'm not going to talk about this in details, but you can basically do a lot of these gates for this quantum computer to run. At the end, these boxes are to basically means measurement. So I want to measure what is the value of the first quantum bit. This is what is the value for the third quantum bit. So you can actually play around with this yourself. So this is on the cloud and free. Of course, this is only 5 quantum bit, so you really cannot do a lot of things. So to give you a sense, with 5 quantum bit quantum computer, you can factorize 15 into 3 by 5. That's the most it can do. But it tells you that it works in principle. So everyone can try this out. Okay, so with that, I would like to thank you for your attention. Question?
I have 2 questions. So the first one is, what's limiting researchers from getting more quantum bits on a chip?
That's a very good question. So I think the biggest one is basically the error. If you think about it, in one sentence, it's just the error. So when you have more quantum bits, the errors just go crazy and crazy. So you just cannot put more of them. Because if you're getting the wrong answer, what's the point? Right?
Okay. And then my second question is, what you said that photons were the kind of like predecessor of the current qubits. What are they using now?
That's also a good question. So the photons are bad for quantum computing because photons can easily be lost, right? Because the photon can just be absorbed by the environment. It's just such a tiny little bit of light there. So it's not a very good quantum computer because the error rates will be very high, and it's very hard to put a lot of photons into the computer. But they're very good for communication. So the photons are now used as a quantum network. So you can use the photons to transmit information between two remote quantum computers. You can use a fiber to do it, or you can do it over free space, over satellite.
So what are the qubits?
So the qubit is just carried by the polarization of the photon, as I just said.
Oh, so it's still...
Yeah, it's still that.
Oh, okay.
It's just not used inside a chip. It's used for communication. Yep.
So at any rate, actually, I understand there are like 7 billion transistors in the processor for quantum computing. And I wonder, say, like, if you could basically touch upon the development of the superconductor material.
Oh yeah, so the superconductor material can be used to make a quantum bit as well. So this is actually, so IBM and Google are both using superconductor to make a quantum bit. So it will be different from this quantum bit composed by the photon we talk about, but it's a more complicated thing. So it's basically a superconductor, so two superconductors separated by a very thin insulator, and that can actually make a quantum bit.
Right, but the material itself is the element?
So it's not just a material, it's really so you can think about this. So it's a current that's flowing in the superconducting ring. So the current, so this is just one example. Not all the superconducting quantum bit works the same, but the example I give you is easier to understand. So the current in the superconducting loop can either be flowing clockwise or counterclockwise, and you use these two different states as your quantum bit of value 0 and 1.
Okay.
And any superposition of these two currents will basically be a superposition of 0 and 1. So that's how it works. Any other questions? Okay.
Interested in what you said with the current state of affairs, the amount of error that's associated with it. Are there hopes that the error can be reduced?
Yeah. So people are constantly trying to lower down the error, and one very promising route is called error correction. So classical computers can also do error correction, right? The simple way is you encode 1 bit of information in 3 bits, right? It's unlikely all of the 3 will basically be wrong. So you use a majority vote. If one of them is wrong, the other 2 are still correct. So that's sort of a naive way of doing error correction. And there are more sophisticated ways. So by using error correction, so even if you have an error of say 1%, I can still correct that error. But if the error is too high, if it's 10%, I think error correction is not going to do much. So that's why researchers are simultaneously trying to lower down the error of these devices. At the same time, they're trying to implement something called error correction scheme. Question?
So what are the main sources of error?
Oh, the main source of error is just all kinds of environmental noises, because these systems are really tiny, right? These quantum particles could be a photon, could be an electron, just a little bit shaking the environment. Could be just an elevator passing through. It could be just the Earth's magnetic field. Anything fluctuating in the air is going to affect these tiny particles, this quantum bit, and could destroy the information. So you have to really shield, your quantum computer well from the environment. Usually they have to put it into the fridge with very cold temperature. Yeah, but there's tons of errors. So it's a really challenging problem. Any other questions? Okay.
Okay, this is a tiny bit technical, but you mentioned that searching on a with a quantum computer has O of the square root of n speed. How is sorting? And if sorting is improved significantly, wouldn't it be faster to sort using a quantum algorithm and then search using binary search, which has
a log n, right?
O log n, which is even faster than O root n?
Probably having a computer science background.
Yes, yes.
Yeah, I think probably the answer is yes. I do have a degree in computer science, but don't trust me too much on that. But I think you can do sort faster as well with these square roots and speed up, and then do whatever this binary search. Yeah. As I said, this quantum search algorithm is very universal, so you can almost speed up any complicated computational task. So this is kind of a consensus among the scientists in this field. Square root speed up is kind of universal. But the question is whether that's worth building a quantum computer.
Well, you could use a quantum computer to sort it, which would probably be faster than O of n log n, and then the O log n classical search, if you're searching through it enough, presumably the classical method would actually be faster once you sort it.
It could be, but you can see the dominating time constant is that square root. And the log n is kind of minimal.
Right.
You can forget about that.
Yeah.
Any other questions?
Just a non-technical question. Where do you see the biggest strides being made in terms of industry or research in this area?
Sorry, can you say it again?
Where do you feel the biggest strides are going to be made? Because you talked about the Japanese.
Oh, you mean? Oh, yeah. We're talking about the biggest. Well, right now it's kind of hard to say because all these leading academic institutions. I came from one of them, which is very good in doing quantum computing in universities. They kind of already have their own company, and a lot of industrial money is flowing into those companies. And so Google is also an example. So the Google Quantum Computing Labs, it's called Quantum Artificial Intelligence Lab, is initially a group running by University of California at Santa Barbara, and the Google sort of just poached them and give them a lot of money, and then they become rich and they're making a lot more progress now. It's because the huge amount of money that's flowing into this. So I think in the future probably this industrial side is going to progress faster than academia. But I sort of see a sort of a complementary thing happening. The academia is less interested in the technical details, but more interested in the theory, like what quantum computers, what's the limit of the quantum computer? That's actually a really interesting question. We talk about all these fascinating applications of quantum computing, but we really haven't talked about what's the limit, right? So what is the computational limit of quantum computing? And that's really a very interesting question because we know this is sort of the limit offered by nature. There's no other thing we know that can run faster than a quantum computer. So if we know the limit of a quantum computer, we know the limit of everything we have in control. Right? So that's sort of like academia is thinking about this question a lot recently. Any other questions? Oh,
does it make sense to put it in vacuum to minimize errors?
Yes, people definitely do that, especially for some atomic qubits. If you are trying to use the atom as a quantum bit, you want to put it in the vacuum. Otherwise, there's going to be tons of atoms in the air that's going to hit the atom and you're gone. And your qubit is gone. So you need the vacuum for sure. You have another question?
So these quantum computers, do they see more as like quantum chips that will like be integrated into computers in general?
That's a good question. So that's why Google and IBM is doing this superconducting circuit quantum chip, because these things can actually be on a chip. But if you're using atoms, it can't be in the chip. You have to be in the vacuum chamber. So that's not favorable to integrate into this classical silicon fabrication process. So that's why big companies are going into this solid state platform.
If there's no more questions, I'd like to thank Dr. Gong again for coming. I'm sure he'd be willing to stay for a little bit, just to talk to about personal questions if you really want to come up here. But thank you guys for coming. Hopefully we'll have another lecture coming up soon this semester. Not in quantum, it will be, I think, string theory is what the next lecture is. Probably, we're still talking with the professor on what he wants to talk about. But hopefully we'll have another one. And this seemed like a good room, but we also got a lot more people than we expected. So we might move to a larger atrium to do the next talk. But thank you for coming.
Yeah, of course.
Hey, so that's not that's going to be
Is it stopped yet?
Never start. Yeah.